Hi, hello everyone. So this is the video dealing with section 2.7, polynomial and rational inequalities. And I've divided this topic into two videos. This is the first part where we go over the definition and solving the polynomial inequalities. And in the next video, we'll do the rational inequalities. Now, for the polynomial inequalities, it is almost identically the same as solving polynomials. So if you remember from your Math 119 course, when we have a polynomial, um, we are going to set the polynomial, whatever the polynomial is, we're going to set the polynomial to 0, and then we're going to use the factoring techniques, the different factoring techniques that we know, greatest common factor, grouping, the trinomials, difference of squares, either sum of cubes or different of cubes, to completely factor the polynomial, and then we're going to apply the zero product rule to find the individual roots, and then we're done. Now, for polynomial inequalities, we don't have the equal sign. So we have a polynomial inequality if we have one of these four inequality symbols. Okay, so instead of the equal sign, I have to have a less than sign, less than or equal, greater than, or greater than or equal sign. So if I do have one of these four, then we call it a polynomial inequality. Okay, and so here's the mathematical definition. So polynomial inequality is any inequality that can be put in one of the four forms: less than 0, greater than 0, less than or equal, greater than or equal. Okay, where the f is any polynomial function. All right, so now that we know the definition, the process is very simple to solve it. It's just like I said, you're going to you're going to first set the polynomial inequality to 0. Okay, so it's either going to be one of these four inequality symbols. So whatever it is on the right side, it has to be 0. So this is our starting point. Then we're going to step 2, we're going to solve pretending that we have the polynomial equal to 0 because we are going to find the roots of the polynomial. Okay, once we find the roots by factoring and using the zero product rule, then the third step, we need to check the values that satisfy the polynomial between each root. So you see this when I solve the polynomial inequality, but just let's pretend now that I have two roots of the polynomial. So let's say one of the roots is -1, the other is 3. Okay, so I'm going to put some dashed lines here for you to see. This is one of the root. This is the second, and here's the real line going toward positive infinity and negative infinity. All right, so I have these two roots of the polynomial. Now, the two roots divide the number line into three sections. This section for values smaller than -1, this section or segment between -1 and 3, this is the second, and here's the third section for values greater than 3. So after I find the roots, I have to pick a value in each of these segments. All right, so I need to pick a value in each of these segments. So in this case, any value less than -1 here would be okay. So for example, I can pick -3. In the second segment, I need to pick a value between -1 and 3. So any value in the middle would be okay. I'm going to pick 0. Okay. And I need to pick a value in the third segment. Any value bigger than 3 would be okay. I'm going to pick 5. So I need to use these three values in the factored polynomial in order to see if that value produces a value according to the inequalities. If it does, then the answer would be true and the solution in that interval is correct. If it is false, then the solution of that interval is incorrect and I remove it from the solution set. Okay? So, and the reason for that is once we determine if the solution is true or false, right? So if the value in the value of f is positive, then if the solution is greater than or equal, it is true. It is the same solution for all of the values in that interval. And the same thing for the opposite. Okay, so once I determine if the solution is true or false for that interval, then the last step is I'm going to write the solution set in interval notation. Okay? And then I will be done with the problem. So the solution for these polynomial inequalities is just like a solution for an inequality that you saw in Math 119, where we have to write the solution set in interval notation. Okay, so here are the steps again. I'm going to erase all of this. And that's okay if it's still not very clear. I'm going to do two problems and it's going to be clear. First, we're going to express the polynomial in less than, equal, less than, greater than, equal to 0 form. Then we're going to solve this polynomial equation. We're going to find the roots of the polynomial equation. Okay. And we are going to choose, once we find the root, we are going to choose a representative number between each root. So this is called a test value. And we're going to determine if the test value is true or false for each case that I may have. Okay, I may have one of these four possible cases. Once I'm done, I am going to write the solution set in interval notation. All right, so these are the 4 steps that we need to take, or 5 in here, if you wanted to be more specific. And I'm going to show you exactly what to do right now. Okay, so both of these examples are taken from the textbook, so you can look at them later in the text if you want to have more details. But I think I'm going to be pretty detailed so that you can follow it here. All right, so the first equation is, inequality is this one right here. Right, so step 1 in my procedure is I have to set the polynomial equal to 0. So I can't have this 15 on the right side. So I need to subtract 15 on both sides. And this would be my starting point. So 2x squared plus x minus 15 greater than 0. So the 2x squared plus x minus 15 is my polynomial. And here's the inequality that I'm trying to check. Now, the technique to solve this is the same technique that you've seen in Math 119. The only technique, even though for quadratic, you could use the quadratic formula, I am going to use factoring to solve this. And this is the technique to factor a trinomial, where we need to use the AC method. Now, I'm not gonna review the AC method here, but if you do need to, you go check online or your previous notes from the Math 119 course, how to factor the trinomial. And so the AC method says I need to find two numbers whose product is A times C. Right? So the polynomial here is in A times AX squared plus BX plus C format. So the A is the coefficient to x squared, the B is the coefficient of x, and the C is the number. Okay, so the product has to be equals A times C or 2 times negative 15. And the sum has to be equal to B, which in this case is positive 1. Now I have to find all of the groups of numbers whose product is 30 and the sum is 1, but we begin with the product. Right now you can find all of them, so 1 and 30, 2 and 15 and so on and so forth. Or if you are able to immediately find the one that satisfies both criteria, go ahead and do it. Okay? So take a look at 6 and 5. The product is 30, but if I want the sum to be positive 1, one of these two values has to be negative. So now 6 and negative 5, I have a product of negative 30 and a sum of positive 1. So this is my correct pair. Once I find the correct pair, I have to rewrite the middle term of the polynomial. So 2x squared. So instead of writing 1x, I am going to write plus 6x minus 5x. I haven't changed anything, right? So the sum of the 6x minus 5x is still positive 1x. But now I am going to be able to factor by grouping. So this is what the AC method is all about. So I group the first two, I group the second two, and I factor the GCF of each separately. So out of the first group, I can factor 2x. I get x plus 3. Out of the second group, I will always factor this sign, minus 5 and x plus 3 greater than 0. I can see that x plus 3 is a common factor, so I will factor it again. So this is the essence of grouping. And in the second factor, I will have 2x minus 5. Now, at this point, the polynomial, the original polynomial here, is completely factored. I need to find the roots now. So I apply the zero product rule that says that when I have two numbers and the product is 0, one of the two is 0. Now remember that even though I'm using this symbol right here, the greater than symbol, I am actually solving x equals to 0. All right? So for now, I am solving this. So I set the first factor to 0, and I will solve for x. I set the second factor to 0, and I'll solve for x. So obviously minus 3 on both sides. This is one root. Add 5 to both sides, and divide everything by 2. And I have the second root. These are the two roots. All right, so this is, I would say, the first part of the problem is to rewrite it in with the 0 on the right. The second part of the problem is finding the roots. We did. Now, the third part is we have to check the intervals. We have to check the intervals to see if our solution satisfy the problem or not in the intervals we're checking. So you're going to write the real line, right? So positive infinity going that way, put the 0 in, and put the roots in, okay? So one of the roots is going to be negative 3, and the other root's going to be 5 over 2, okay? So here they are. So I'm going to put here negative 3, and I am going to put here 5 over 2, okay? And again, the problem, the real line is divided into 3 segments. This is the first one. This is the second one. And this segment is the third one. I need to pick a value in each of these segments to test. So in the middle, I'm going to pick 0. It could be any value in here, but not the boundary values, not negative 3 and not 5 over 2. So 0 is fine. If you wanted to pick 1 is fine, or negative 1 is also fine. I'm going to pick 0 because it's easy. I need to pick a value here somewhere. Now 5 over 2 is 2.5, so I'm going to pick 3. Okay, but you could pick 5 or 7 or 8 or 10. So if you want, instead of 3, here, pick 5. I'm going to pick 5. And I need to pick a value in the first segment. I'm going to pick -5. All right. I need to test all these three values. So I'm going to test the -5. I'm going to test the 0. And I am going to test the number 5. So I'm going to test this, this, and that. Now, to test these values, you are going to go to the factored polynomial and the original inequality symbol. Okay, so the original inequality symbol is greater than. So I'm going to write it here in factored form, x plus 3 to x minus 5 greater than 0. This is where you're going to check your values. This is what you're going to do. You need to know the sign of each factor after you replace the number. So I'm going to replace the 5 here and here. So -5 plus 3 is -2. Okay. I'm only interested in the sign, not the actual number, positive or negative. So this is -5 times 2, -10, minus 5, -15. Greater than 0. And now you have to decide if this times this is greater than 0. Well, -2 times -15 is +30, is greater than 0. Yeah, that's okay. Now, this means that this interval right here, is a solution to the problem. Solution. Okay, because a number in this interval satisfies the solution. So the whole interval is a solution. I'm going to test this 0. I'm going to test this 0. So again, I'm going to use this to test. So 0 plus 3, obviously 3. 2 times 0, 0 minus 5, -5, greater than 0. So 3 times -5 is -15. Is -15 greater than 0? No. So this interval is not a solution. So I don't write it in. Now I have to test the 5. So I'm going to get 5, and I'm going to replace in x here and 2x there. So 5 plus 3, right? Remember, I am here. I'm using this. So 5 plus 3, 8. And 2 times 5, 10, minus 5, 5. Is 8 times 5 greater than 0? Yes, it is. It's 40. So this interval is a solution. So this interval is a solution. So I found two intervals that are solutions. So now my last step is to write the solution in interval notation. Okay, again, I'm not going to review the details of interval notation, but I am going from -infinity on the first interval to -3. And you don't need to use the union symbol. A comma is just fine. And I'm going from 5/2 to +infinity. So this is the solution to this problem right here. Okay, so the three parts. First, you set it with the 0 on the right. Second, you fully factor the polynomial. And third, you check the factors in the intervals you have to write the final interval notation. All right, so this is the first problem. Okay, so let's do the second problem. I'm going to erase all of this because we need the space for the second one. Second one is identical to this. So here's the second problem. So again, first step is to make the polynomial equal to 0. So I need to subtract 4x, and subtract 4 on both sides. So I'm going to end up with x cubed plus x squared minus 4x minus 4 less than or equal to 0. At this point, I have to factor the polynomial on the left, and I know that the factoring technique is factor by grouping. So I'm going to group the first two, group the second two. Out of the first group, I factor an x squared. Right, so this is x plus 1. Out of the second group, I factor the minus 4, x plus 1. I see the x plus 1 is a common factor. I factor it again, and I get x squared minus 4. And I realize, and I must realize, that this is difference of squares. So there's another factor in here. So I'm going to factor that. Again, I am now reviewing difference of squares. So that we have to remember how to do. But if you don't remember, you can always spend 5 minutes or so, 10 minutes online or in your taking a look at the notes from your previous course to remember how to do this. So now at this point, the polynomial is fully factored. I'm going to apply the zero product rule and set each factor to 0 and solve for x. This is very easy. You don't even need to do this step. You can do it in your head. And solve each one individually. So the first case, I'm going to subtract 1 on both sides. Second case, I'm going to subtract 2 on both sides. Third case, I'm going to add 2 to both sides. And I got the 3 roots. All right, so this is probably the most time-consuming part, but it didn't take that long. And now I am going to test the intervals or test the values, right? For that, I need to write the real line. I'm going to put in the 0, and I'm going to put each of these roots in. All right, so -1 is here. -2 is there, and I'm going to put 2 here. Okay, so -2. You don't need to put these dashed lines. I'm putting them here so that you can see the interval clearly. And now you can see that I have 4 intervals, right? I have this one. I have this one here. I have this one. And I have that one. So 4, 3, 2, and 1. So 4 intervals. I need to pick a value in each interval to test. So pick a value here after 2 to test. I'm going to pick 5 again. Between -1 and 2, I am going to pick 0. This is easy. Less than -2, I'm going to pick -5 again. And I need to pick a value in here between -2 and -1. So I'm going to write -1.5. Okay. And I need to test all these 4 values. So test. So negative, and you're going to test it on the factor polynomial. Okay. So -5, -1.5, 0, and 5. I need to test all 4. So you're going to replace these values in the polynomial here, where you see the x. Now, keep in mind, again, I only need to know if each factor is positive or negative. I'm not interested in the value, the numerical value. So this is the way I'm going to write it. This is a simplified notation from the previous problem. So -5 plus 1 is -4. So instead of writing -4, I'm just going to write negative. Okay. Negative 5 plus 1 is negative 4. I don't care for the actual numerical value. I just care if it's positive or negative. Negative. Negative 5 plus 2, negative 3. So negative. Negative 5 minus 2, negative 7, also negative. And now write the sign, which is less than or equal to 0. So multiply all of these three minuses. So minus times a minus positive times a minus negative. Yeah, that's true. So there's a solution here on this side. All right, so there's a solution. There's a solution here. Okay. Let's test the negative 1.5. So we go back into the polynomial factor form. So negative 1.5 plus 1 is negative, right? Negative 0.5. Negative 1.5 plus 2 is positive, right? Positive 1/2. And negative 1.5 minus 2 is negative. So negative times a negative is a positive, times a positive is a positive. So this is false. So there's no solution here. Let's test the 0. Again, we go back into the factor form. So 0 plus 1 is 1, which is positive. 0 plus 2 is 2, which is positive. And 0 minus 2 is minus 2, which is negative. So positive times a positive is positive, times a negative is negative. So that is true. So there is a solution here. And then let's test the last interval, which is the number 5. So we pick the 5 and we go back here again. So 5 plus 1, 6, positive. 5 plus 2, 7, positive. 5 minus 2, 3, everything positive. Positive times a positive times a positive. It's positive, not less than or equal to 0. So this is false. And there is no solution here. So the two intervals now, the solution is this one and that one. So now I have to write that in interval notation. So here's my solution. Okay, keep in mind that the inequality is less than or equal. So in the previous problem, I didn't have an equal sign. Now I do. Okay, so when you write your solution, let me just erase this. When you write your solution now, for example, in this interval, you're going from negative infinity to negative 2, but the negative 2 is included because of the equal sign. So you have to use bracket here, not parentheses. The parentheses is not included. And the same thing goes for these two boundary points. So the solution goes from negative 1 to 2, but both intervals are included. So you have to put the bracket on each. Do not put the parentheses because this would mean that the endpoints are not included. This is only true if the sign was this, right? Less than. But because it's less than or equal, you have to include the endpoint. So this is the solution for our problem. Again, you don't need to write the union symbol. It's okay. Just put a comma between the two, and it's perfectly fine. Okay? So this is how you solve polynomial inequalities, right? So put them in this format with the 0 on the right, find the roots, and then test the points. And then finally write the answer in interval notation.